Our solution is an unmanned aerial vehicle, or as it is known to the commercial public, a drone equipped with an infrared camera and computer vision tracking algorithm. The goal of this project is to send in these vehicles to seek out targets in military settings. The infrared imaging capabilities on board will help with target tracking even in low light settings, such as at night. Here is how the system works. The IR camera on board the drone sends signals back to the ground station wirelessly through an FPV, or first-person view wireless system. The receiving end of the FPV system is simply attached to a computer via USB. The ground station computer will be outfitted with a computer vision control software, which will guide the drone's movements autonomously based on an object tracking algorithm. Integrating with DroneKit, a 3DR Python developer library which integrates Python script functionality with drone movement, the computer vision software will then send commands to the drone to fly it. The user will have 3 options for flight in this system: normal joystick controlled flight, waypoint flight, or autonomous object tracking. The user can also override the autonomous mode at any time and regain control simply by quitting the tracking algorithm. This UAV has also been programmed with a return home feature, which allows it to fly and land back where it started its mission.
The first-person view, or FPV subsystem, is where the communication happens between the infrared camera and the image analytics software. The infrared camera picks up infrared signatures from its camera module and infrared sensor and formats these images as digital. The video output module is made up of a Raspberry Pi Zero that was programmed specifically for interfacing with this camera. This microcontroller has a micro SD card with a full image uploaded onto it, which reformats the camera images from digital to analog for transmission. For transmission, we use the TS-832 from Wolfwhoop. With a frequency set to 1 and channel set to 7, it takes the analog images from the Raspberry Pi Zero and wirelessly sends them to the receiver, the RC-832 by Wolfwhoop. The receiver is set to frequency 2 and channel 1. The video output from here comes out through AV cables, which is connected to an EasyCap converter. This converts an AV connection to a USB connection to be read into the ground station laptop and into the tracking program.
Since conventional IR cameras can be priced in the thousands of dollars, we needed a subsystem which would cost under the $500 that was allocated for our budget. This subsystem was created based on an open-source GitHub repository design. Its principal components include a Lepton 3.0 infrared sensor, a Teensy 3.6 microcontroller, a spot sensor to measure relative temperature, and an Arducam camera module. This camera, when used in live stream mode, can broadcast infrared video at about 3 to 5 FPS, or frames per second, with a range of about 20 feet. The RGB camera, which can take still color images with up to 5 megapixel resolution, is a bonus feature which can be activated with the push of a button, which saves the image files to an onboard SD card. This subsystem integrates with the Raspberry Pi base output module previously mentioned.
The image analytics software uses Python 2.7, OpenCV3, and tkinter to provide an interactive interface for the user to select a target on screen, track the target, have the option to stop tracking, command the drone to return home, have the option to change from infrared to RGB, or vice versa, and gives information about the approximate location of the target, UAV battery level, and UAV mode. Here is the tracking algorithm logic. When the program starts, it waits for the user to create bounding points of the region of interest by left-clicking and dragging from the top left to the bottom right to create a box around the target. If there are no points, then the user may exit the program or send the UAV back to the launching site if it's deployed. Once the user makes the bounding points, the program gathers these points and sets up the region of interest information such as histogram and color mapping for the tracking algorithm. For this application, we used a common tracking algorithm called mean-shift. Mean-shift looks at the centroid of the box and locates the area with the maximum pixel density. When the pixels move, the centroid moves with them and changes the location of the bounds to the new centroid. If during this process the user presses the Stop Tracking button, the mean-shift algorithm will stop and the program will go back to just displaying the feed without any region of interest bounding box. From here, again, the user has the option to exit the program or send the UAV back to its launching site.
The central component of the system is a UAV, or unmanned aerial vehicle, or, as it is known to the commercial public, a drone. The most challenging part of this project was locating an open-source, ready-to-fly unit, which could be integrated with the computer vision and infrared camera inputs. In the end, we decided on a 3DR Solo, possibly the most inexpensive, open-source quadcopter on the market at the moment. The Solo, with dual onboard computers that run Linux, is a smart drone that can be reprogrammed with Python and integrates with the ground station computer vision code previously mentioned. The Python script library that makes this integration possible is DroneKit, an open-source package also created by 3DR, which translates the commands from the computer vision software into the drone's movements. The Solo has an onboard Wi-Fi that connects to a joystick controller, phone app, and ground station. Together, these make the most inexpensive open-source system on the market.